Okay, today we'll be talking about the transparent latch that drives the Nixie tube logic. Um, why do I want a transparent latch? Well, because it's nice to see the Nixie tube digits change as you dial the number. Um, these are the design parameters for the latch. It has to be 4 bits because I want to be able to count from 1 to 10. Because the 10 is the 0, so I need to include the 10. Input logic 0 can either be 12 volts or floating. I don't really care which one of the two. Logic 1 has to be ground. For the output, logic 0 has to be plus 12 volts because I'll need this for the comparator to check if the entered code is correct, and logic 0 is ground. The latch signal I also don't really care about. It can be from 0 to 12 volts, 12 volts to 0, floating to 0 or floating to 12 volts. This signal will be coming from a double pole, double throw relay, so I've plenty of options to choose from. As I said before, the 4-bit binary input is 1 to 10, or in binary it will be 001 to 1010. The output 000 or the input 000 I don't really care about, but preferably there it shouldn't latch, because if a latch signal is received and the inputs are 000, something went wrong in the counter. And I'll be using the same double pole, double throw little relays, so just using them and some other components, diodes, resistors and capacitors. I managed to get this circuit down to 6 relays, so if you want a challenge, you can try and design the circuit yourself before continuing to watch this video. Okay, so here's the schematic of the transparent latch that I created. The data input and the data output is represented by a logic level being ground and a logic level 0 being 12 volts. The input of the latch is a 12 volt signal, and when there's no signal, this line will just be left floating. The transparent bit of the latch is just this data in being connected to the data out through this switch being in the up position. When the latch is triggered, this switch will move in the down position on this side. And depending on the state of this relay, the data output is either connected to negative when the relay is activated, or the data output is connected to positive when the relay is not activated. So how does the latching mechanism work? When the latching signal occurs, this relay will be immediately pulled to 12 volts on this side. The 12 volts will also go to this relay, but it will be delayed shortly by this RC circuit. So this relay will switch on a short time after the latch will go high. This is to give this relay the time to set into its correct position before this relay latches the circuit. So let's have a look what happens when there is a 12 volt signal or a logic 0 on the data input. This switch will remain up position for the first few milliseconds, and the data will be out here 12 volts. For now it doesn't do anything on this switch. It will become 12 volts on this switch, so there's no potential difference, and this switch will remain up. After a short while, when this relay closes, this 12 volts is then going through this side to the output, and it will remain there. When the input is 0 and this relay is activated, this here will be 0 volts. So there's a potential difference and the relay will close. And the output will be connected to ground through this switch. And after a short while, this one will close. This switch will go down, disconnecting the input and basically connecting this side to a floating point because the 12 volts will be in a down position. This is important because this 12 volts also feeds back to the relay to latch it in position. When the latch signal disappears, this relay will still get its 12 volts from this source. Now it gets a little bit tricky. Let's say all the inputs are plus 12 volts, so all are logic 0. Then none of these relays will switch because they'll all be at 12 volts of the 4 stages. So how can this relay then switch? Well, it gets 12 volts from here, from the latch. These relays don't do anything. This relay will activate it and it will go down, connecting to the 12 volt signal here on all 4 bits. But once the latch signal of 12 volts disappears here, this one will go floating. This one will be at 12 volts. These relays still remain in the up position, but there's no current holding this relay down because this side will be floating, this side will be negative. There's no connection to 12 volts on any of the 4 circuits, meaning that the data here will be switched back through to the output. So basically this circuit won't latch when there's a zero, a digit 0 on the input, which is 0, 0, 0 in binary. It won't trigger the latch, which is important for this circuit. In any other case, at least one of the digits will be grounded, will be a logic 1, so it will be grounded, and at least one of the relays will connect the latch line to 12 volts, meaning these relays will always latch. These guys are 2 relays connected in parallel to switch 4 input lines. So that will be data in 1. This can be used as data in 2. We can also have a look at this diode here and why it's there. Let's say we have a logic 0 on the data input, which means this will be connected to 12 volts. This can flow past the relay through the freewheeling diode into the latch circuitry line, triggering this relay without the latch signal being activated. That's why we have this little diode here. This is a complete circuit of the 4-bit latch. These relays switch the individual bits between input and output line and the latch state. And these 2 are the 2 trigger relays. They're connected in parallel. For the time delay circuit, I took a little bit of experimentation. I used 22 microfarads and 90 ohm resistor. I actually used 2 180 ohm resistors in parallel. It's important that these relays only switch after these relays had time enough to switch and settle. If it takes too long for this to activate these 2 relays, then somebody might be dialing in the next number and the latch signal will be lost before they are triggered. So this was kind of experimentally determined, these values. Here we have the plan for making the connections on the relays. Fortunately, I've already built one, so we can have a look and see how to read this circuit. All these angled bits here, they mean that these wires are at the level higher than the plane of the relays. So for example, this one goes up, across, over this positive line and then back down. That's this line right here. As you can see, it goes up. Same for these zigzaggedy lines. That's these guys here. And this last one is down here, made a little bit of a scribble. All these diodes, light emitting diodes, their connections are actually at the bottom here. So this resistor goes from the top next to the relay down to the LED. This connection is level with the relays, which is this one here, going all the way up to there, and the connection to the LED is from this point going straight down. The ground line I've run behind the relays, so that's that one down here, going slightly up again for each connection. There's also a connection from the middle going down, which is this line here, this dotted line going all the way in between the two middle relays, and it resurfaces on this side, connecting the capacitor to ground. Another tricky bit, it's these resistors here. Basically it's the 2 times 180 ohm connecting the capacitor for the time delay between these two relays that switch between the transparent and the latch. That line is running from the latch line up here, down, across and back up here. It's a little bit tricky to see, but here's the 2 resistors, and at the bottom they're connected to the latch line, which is joined right there. So this latch line and ground are running next to each other, so make sure you insulate one of the lines so they don't short circuit underneath. So I hope that this schematic is a little bit clear, or clear enough if anybody wants to replicate it to end up with this as a result.